Well, hello everybody, and welcome again to another OpenShift Commons briefing. This time, we're going to be talking about OpenShift container storage. That's what that OCS4 stands for. And we have Marcel Hergaarden, who's the storage BU evangelist from Red Hat, with us to give us an overview and answer Q&A afterwards. So we're going to let him give us the overview. There'll be live Q&A at the end. The slides will be available afterwards, as well as the video will be up on our YouTube channel and posted on the OpenShift.com blog. So without any further ado, Marcel, how about if you introduce yourself and give us our overview?
Will do. Thanks a lot. Okay, so my name is Marcel Hergaarden. I'm Solution Architect, Storage BU Evangelist in Red Hat nowadays. I have been solution architect for storage, among others, for about 7.5 years, and I recently joined the storage BU. And from within that position, I'm happy enough to tell you today about OCS4, OpenShift Container Storage, Red Hat OpenShift Container Storage, to give you an introduction on what it is, how it relates to OpenShift, and how things work. I'm based in the Netherlands, so for me it's good evening. Depending on your time zone, it might be morning. So good morning, good evening, wherever you are. I think we can start. So this is the agenda for this session today. It's about OCS, OpenShift Container Storage. We'll have a look at the application behavior nowadays, and then why storage involvement is crucial in that regard. We'll have a look at Red Hat OpenShift Container Storage, of course, the technology that it uses. The stack is Rook, nooban, Ceph. We'll dive into that in more detail. For the people who are not familiar with Ceph, I also have a short Ceph 101 introduction so that you know why we use Ceph, what is under the hood, etc. We'll have a look at OCS features, components, sizings, and guidelines. And then last but not least, the roadmap, and then I have prepared a few slides on how it actually works to set it all up, to make it up and running inside your OpenShift cluster, so that you get a bit of an idea on how to implement this and really how easy it is to get things rolling and why it's important. So this is the agenda for this session. I have a lot of slides, so I hope we will make it through the hour. And I would encourage, if you have any questions, then it would be great if you could, save them until the end of the session, so that we then can go through it. If you feel like it's really, really urgent, then we can, maybe interrupt. Okay. So first of all, let's have a look at application properties and the behavior. As you know, back in the old school days, and I'm really talking about the 90s and the 2000s here, we had our operating system. And with that operating system, we had our operating system dependencies that were, actually needed for an application to run. So you had the bare operating system dependencies on top, and then the application. That was the traditional way that we were used to run applications, either whether it was on bare metal or on virtual machine. That was the way things went, actually. Nowadays, in a modern application landscape, we are working with container pods, and same in OpenShift, you have the container host, where actually the engine runs on, and then on top of the host, we have our containers, and inside the container, the word literally says it contains something. It contains the application, including all the dependencies it needs to run. And this makes the application actually highly portable, so that we can move it across other hosts. Well, you know how it works, but it's just a sort of introduction, the difference between traditional and modern application. So with this modern application, there is no longer a monolithic application. So we cut functionalities up in multiple pieces, and each piece actually is run by a separate container. And this enables us for updating applications bit by bit and piece by piece without impacting the service. So it's getting way more flexible. Well, this is actually the idea of microservices, where containers encapsulate those microservices. So we can also, evolve independently, so each component can be updated or replaced while the application keeps alive. However, a container is always a system process. It's not like black magic or so. It's a process that actually runs on your system, and a system process that can die, that can fail for whatever reason. So this is exactly the reason why container storage is essential, and why containerized applications do need storage. Namely, a container app is not persistent by default. So when the container application dies or struggles, whatever, then there is a chance that you will lose the data. Think of it as, in this example, as a lamp. We switch on the lamp, there is light, and when the lamp goes defect, there is no light anymore. The light is gone. It's maybe a strange, comparison, but just trying to make it clear. So, and in somewhat more detail, we have our infrastructure, host OS, containerized platform. On top of that, that's where the containers run, or the pods in our case, and inside the pods we have the container. Well, how is this container composed? It all starts with a base layer. So there is an operating system base layer where everything starts from. Then we got the library and binaries that the application actually needs to have to be able to run, its dependencies, if you will. Then there's the application. And on the top layer, as you see, those are layers inside the containers. And the top layer, that's the only layer that is actually writable, because all the other layers are read-only. So that means that they are immutable. You cannot write to them, you cannot change them, and only the top layer, that's a writable layer. And this is exactly the place where the application state lives. So if an application runs, it creates state perhaps, or it has data, and that data is being stored in the top layer. And that's the writable layer. So imagine that if this container dies or something happens, then it's always gone, including this writable layer, because that's kind of volatile storage. And that means that we need to do something, and we need to mount that top layer to a storage system outside the container to make sure that if something happens, that all the data that was, that container bringing along, that it survives the container. In other words, it is persistent and it stays there, so that we can replace the container and the new container can, continue with the data that was already produced by his previous one. So there are multiple ways of using storage in containers. The most common used one is actually the persistent file store. That's also named RWX. And RWX, that actually means read, write, many. And that means that multiple containers can connect to the same file storage in order to use this. So the container application state is held within that persistent file storage. Remember the previous slide where I showed you the top layer that was actually writable. Well, this one is actually being mounted to the storage system, so that the data lives outside the container on a persistent file store. And this is what we offer, among others, with OpenShift Container Storage. Then there's another storage type, and that's block storage for containers, and that's also named RWO, and that means read write once, and that means that only one container can have access to that storage, and it's uniquely consumed by that one container. And this is a specific storage type being used for workload that requires performance. And then you could think of database workloads, logging, Elastic, those kind of things where you really need performance, and a file system is not always capable of delivering the optimal performance for those kind of workloads. And that's where we have block storage that is more powerful, can have more I/O sequence compared to file storage. So that's file and block. And then there's a third one that's named object storage. And this is also seen in public clouds, and that's named S3 storage, for instance, S3 in AWS. And this is where we place objects compared with a label that has information on that object. Well, a simple example to define what object storage is: everybody has perhaps once in his life used Google Drive, for instance, where you store your documents and so on. So what's actually in there are objects. So your document or the file that you put in there is an object that lives in an object store, and you can pull it, you can open it, and it's not actually a file system. But if you might make the comparison between a file system and an object store, then the object would actually be the files, and the folders, the directories would be the buckets. So in object storage we work with buckets. Buckets is, for instance, the folder where the objects live in. And if you are talking file system, then it's a folder directory structure with files within. Object storage has buckets, and objects live within a bucket. We can have lots of those buckets. Later, we go into more detail on this. And then there is also a fourth thing, and that's actually the registry store. So if we start a container, then it's actually being started from an image. So a container, remember the slide where we had the immutable layers, so the read-only layers, those are part of a image. So this image lives in the registry store. So if you want to start a container, it's getting pulled from the registry store and then started as a container. This registry store, however, may by default not sit on redundant storage. So if you install OpenShift just on a server system, let's say not in cloud, but on a bare metal system, then chances are that the registry would live on a not redundant storage. And that means that if that storage piece, dies or goes away for whatever reasons or get problems, then it could easily happen that your registry is no longer accessible, which means in practice that you could not longer start new container workloads. So that's pretty important. And actually OCS can fix this for you. So if you run your registry on OCS, then your registry content is actually replicated, and it's present multiple times. So if something goes wrong, then there is also a second and a third chance, actually. So then let's have a look at OpenShift container storage. 3 bullets here. Why? Why OpenShift container storage? The main reason is that OpenShift stateful applications, and stateful means that applications that produce state or produce data, they need a complete data and storage management platform. So if we don't have storage, then the state will be vanished if something happens and we have an issue. So what are we actually delivering with OpenShift container storage? A seamless and intuitive developer and storage experience. Well, those are nice words. What does it mean? As a developer working on your programming, you don't want to worry about storage bits and pieces. It just needs to be there. It needs to work. It needs to be reliable, and it needs to be seamless and intuitive. So actually, it just needs to work, and you don't want to bother about, those details, about all nitty-gritty stuff. You just want to have reliable storage, and it needs to work. How are we doing this? And that's the third one. We do this by using Red Hat Ceph storage combined with Kubernetes-centric Rook, and that's an open source project, and nooban. And of course, we will go into more detail. So this is literally about what is OpenShift container storage is about, and the main reasons. So with the development of this product, there were actually some themes, 3 themes, and the main one is portability, and portability in a sense that we wanted to have seamless data placement and access across multiple clouds. And a cloud could be a private cloud on your premise, a hybrid cloud combination, public one like IBM, AWS, Azure is used a lot in the the continent where I live, Google Cloud, whatever. So you want to have the seamless data placement and the same experience. So for hybrid and multi-cloud data, it offers protection for your data, a consistent set of management tools across cloud. What does this mean? If I'm inside AWS, there is EBS storage, there is S3 storage, and I need to know how that works. If I'm in Azure, there's another mechanism that offers the same functionality, but I need to be aware of how this works. If I'm in Google, then there are other mechanisms again, other ways of addressing storage, and you would have to learn all of them and maintain that knowledge because, but you don't want to worry about that. Because if you use OCS, then you have one platform regardless of what's underneath it, and it's the same way of working. It's a consistent set of working with the tools, and there is no specific knowledge on specifics that provider actually has. Second thing was simplicity. So a fully integrated OpenShift day 1 and day 2. Well, what does it mean? Day one is actually the day that you install the stuff. There's a full integration, and day two is actually maintaining the stuff, the management of the environment. That we wanted it to be really simple, and you don't have to be a storage expert or a Ceph guru to be able to install this. A seamless storage provisioning for file, block, and object. Well, I mentioned before the three different types of container storage, which could be file, block, or object, and it should all be the same experience, easy and simple to get this rolling. And as a developer, again, you don't want to worry about the details underneath. It just needs to work, and that's exactly what OCS delivers. And then third, the skill. It needs to be able to support traditional and both emerging workloads. So the traditional stuff like databases and so on, but also the new workloads, and in an easy manner and scalable manner. So you can start really small, and if you need more and more capacity, and then you can grow with your needs. Last but not least, easily share data across different locations and platforms. We'll come to that later on, how that actually works. So Red Hat OpenShift Container Storage actually runs in all possible infrastructure environments. What does it mean? It literally runs everywhere where OpenShift can run. So that's in that same manner OpenShift storage can run. Then there will be no real vendor lock-in. So that means that you are not dependent on one specific type or vendor of storage, as it can sit on top of all different kind of storage resources, even existing ones that you already may have in your company, and you can just reuse your already made investment and make this the same experience everywhere, no matter where you run. Second, it needs to be efficient. So the use of automation to make things efficient, increase utilization of your existing storage resources. Of course, you could use whatever you have already in-house, but then there's always a lot of management around it and housekeeping, maintaining the stuff. And this is in OCS all automized, and it's all also more efficient use of the things you have. And it would need to meet all the container application storage needs. So that could be, again, file, block, or object. Depending on the application that you use, it has a certain need. If you have an existing storage system, often it can only address one or two of those needs, but not all three. And then you need to have a second or a third solution to be able to address everything. And with OpenShift Container Storage, you can actually offer all types of storage that you would want to need with a container application. And on the back end, it just consumes block storage. So it consumes disks or a SAN or whatever you have available, and then there's OCS. And on top of that, we can address all needs that you would want to have. Scalability, been there a lot. Been there somewhat in the previous slide. You can start small and scale to future needs. Always balanced and optimized. We'll go there in a bit, how that works and how that's being taken care of. And it can actually handle petabytes of data. So that's really lots, and it does that in a very nice way. So having a look at the technology stack. So there are, of course, open source products being used in OCS. And those are Rook. We'll go in more detail on this later. It's Ceph, the storage system. And then there's a relatively new one that's named nooban. And nooban, that's where we have our multi-cloud object gateway. And that one consumes nooban technology and delivers functionalities on top of that. So that has all to do with object storage, and we will go into somewhat more detail on this in the next slides. So as you may notice, those solutions are all boxed in this slide, and that's for a particular reason, because each component is able to run as a container, and inside OpenShift it actually runs as a container. So that means that it's completely compatible and it integrates with OpenShift, since all these things run as a container inside OpenShift. So let's have a look at Rook. So what is Rook all about? Rook is actually, like I said, a community project. And what it delivers is a cloud-native storage orchestrator, which takes care of automated deployment and lifecycle management. Those are a lot of words. What does it mean? It actually deploys Ceph for you, and people that may have worked with Ceph in the past may think like Ceph is a very complex product. You need to be well aware on how it works, the different components, how to configure, all these kind of things. We will go there later on. And the nice thing with Rook is that it's completely abstracted away. So you don't have to worry about Ceph. You don't have to have specific Ceph knowledge, actually, because Rook will take care of this. And Rook will do the bootstrapping of the system. So it will set up Ceph for you. It will configure it. It will provision it, scale it, upgrade, migrate stuff within Ceph. Disaster recovery, all those things are actually taken care of by Rook. So in other words, you don't have to be a detailed expert on Ceph storage in order to be able to use OCS. So Rook is a very nice orchestrator thingy that actually takes care of the complexity of Ceph, so that we can just have the benefit of Ceph, but don't have the burden to, to be an expert and know all about it, because it can really get tough. On the bottom of the slide, there's the link to Rook.io. That's the community project. And if you go there, you may notice that Rook does more than Ceph only, but in the context of Red Hat OpenShift Container Storage, that's where we purpose Rook as the orchestrator for Ceph storage. And this slide actually illustrates that more or less. So on the bottom of the slide, you see the OCS pods, OpenShift Container Storage pods, that actually run Ceph. This is Ceph functionality. So in Ceph we have months, we have OSDs. Don't worry if you don't know what it is, because I will go into detail to explain to you what it's for. There's the MCG is the multi-cloud gateway, also runs as a pod inside OpenShift. And don't worry about it. It's all being taken care of by Rook. And as you know, an operator always uses the best practices, the best way of setting things up, and making things available in the way we would want it to happen. So that's all taken care of by Rook. So again, we have block, file, and object storage. Applications can do a volume claim based on block, and that's being handled by OCS. We can also have a volume claim on file storage, and then there is something new here, and that's an object bucket claim. Remember, I made this weird comparison about the file system and objects, so that you have buckets as your folders, and the objects would be the files then. So an object bucket is something that may be consumed by an application. Well, with OCS, you can actually claim a bucket directly onto the application. And that means that you don't have to travel, over an HTTP path API to place your objects in a way like S3, but you can directly connect to a bucket on the app itself. So you can actually claim a bucket directly onto the app. And this is a real nice functionality, and more applications use actually object storage nowadays. It's pretty common, and well, this is a very nice way forward. Last but not least, object storage, of course, that remains possible to talk like S3. The same as you have in AWS, we can have similar functionality, and the nice thing is that's also completely compatible with Amazon AWS. So the benefits of Rook. It's actually the setup, day one and day two management tasks. Those are completely orchestrated and abstracted by the Rook operator. It abstracts complex Ceph setup tasks. It simplifies the setup and the maintenance of OCS clusters for you. So don't worry, there is no, real complex stuff for you to take care of. It's just install the thing and it will work in the best way, because it has the best practices implemented inside this operator. And it can actually be deployed anywhere, so that you have the same experience across the hybrid cloud. So no matter where you run, so where it sits, it's the same experience, either if it's on on-prem, or if it's in AWS, or it runs on another provider. It's the same experience, the same way of working. There is no specifics for one or the other infrastructure. Then let's have a look at nooba. Nooba technology, I should say, because it's a technology. And the product that Red Hat offers is named Multi-Cloud Object Gateway. And I put it out on the slide here, powered by nooba. Well, what does it do? What is it all about? It actually provides you with an S3 endpoint. So that means that your containerized application, your app on OpenShift that needs S3 storage will talk to a nooba endpoint. So that's the S3 interface that the application talks to. And it's this way, it's the same across whatever backend infrastructure you're using. So, like I said, AWS has S3, Azure has something else, Google has its own implementation, and then you would need to be aware of all these, different ways of connecting to that S3 storage. By nooba, you have the same singular S3 functionality endpoint across all these infrastructures. So that's the benefit. I'll show you in a later slide what that means and how that actually relates. And what's the functionality being offered by this? Well, it's a multi-cloud object gateway. That means that you can read and write data across multiple clouds. We can even replicate data across multiple clouds. So that means if you have an OpenShift running on AWS and you write data there, the same data can be accessible for another cluster at another location, even in another cloud. So that's really something very nice and useful that lots of customers are asking for, those kind of functionality. The good thing here, again, is that it virtualizes and abstracts any kind of existing storage resources. So whatever you already may have in-house, and that could be a storage system of vendor X or Y, it doesn't matter. It can even be shared storage, dedicated, physical, virtual. It could be even public cloud or private cloud storage. So what it all can be used as a backend to nooba, so to the multi-cloud gateway. So if you have an existing storage instance or storage system already available and you have capacity on it, you can still use it in OCS and have nooba, make use of that. And then on the top of nooba, you have your S3 endpoint. So even if the backend is a NAS or a SAN, whatever, so it abstracts and translates the functionality. And then there's also control over your data placement. So you can have policies inside nooba that actually place data based on security, strategy, cost considerations, and all per application. So on the granularity of an application, that means per application you can have a policy that defines where its data will end up. So suppose an application runs on AWS, then you could say, I want to have the data of this application stored inside AWS, but also in a secondary location or a third, or those kind of things. That's all capable with the multi-cloud gateway powered by nooba. This is more, from a graphical perspective, what it looks like. So we have an OpenShift cluster. Excuse me. There are 3 applications here, 3 different applications that all talk to the same S3 API powered by nooba, provided by nooba, I should say. So nooba provides the S3 API, and the data that actually gets into this API can end up in multi-cloud buckets. So that can end up in a bucket that's actually replicates across multiple, public clouds. Pardon. And you can also have hybrid buckets. That means that it can write to local storage and in addition to public cloud storage. And we can have multi-site buckets. So that means the data put onto that S3 API, depending on the policy you have defined per application, can end up somewhere that the policy defines. So I hope this makes a little bit sense. So now you don't specifically write to an AWS S3 API or a Google one or a Microsoft Azure one. So no, you write to an S3 API that is provided by nooba on the front end, and the back end of nooba, that's the piece that connects to whatever storage resources behind, in the infrastructure. For the application, from the application perspective, you will always have the same functionality, the same interface, no matter what's, in the back end. How does this work? How is Nooba composed? Let's start on the left side of the screen. There's the Nooba core. That's the brain, more or less. The brain that actually takes care of all the stuff that happens inside the multi-cloud gateway. It takes care of optimized utilization. It takes care of resilience. It also takes care of the performance. So it can actually, cluster together. You can have multiple instances that work together. It takes care of data locality. That means if you want to pull or retrieve data, then this guy will actually make sure that the first path it will check will come from the local data. And so if you have multiple locations, it will not reach out to the location somewhere, at the other end of the world and then get the data. Even if it's nearby, it will get the nearest by data, so locality in that regards, economics, etc. Going to the right side of the screen, that's the scalable endpoint. So this is actually the S3 or Lambda API. Lambda is actually a serverless functionality, which is something that Nooba also can deliver. You can create some serverless functions. So that means you trigger something and a function gets called. That's also another thing that's capable with Nooba. And this endpoint is scalable, which means that you can have multiple of them. So there will never be a bottleneck or a single point of failure, because you can actually scale this and have multiple of these guys that actually load balance or work together. What does it do? It authenticates. It authenticates against the application before you can enter it. It chunks the data, so it actually cuts up the data in multiple chunks. Then it does deduplication, and dedupe actually means that it gets rid of all double stuff. So suppose you have a lot of similar data that has a similar content, then will just store only the unique stuff. So only blocks that are unique will be actually stored. In addition to that, it will compress the data. So it will first chunk it up in pieces, then it will get rid of the doubles, then it will actually compress, squeeze it all together, and then it's also possible to encrypt that data. So to set an encryption on it, and then one of the questions that's often being asked, hey, how about the encryption key? Yes, you as a customer can define that, and you can actually maintain your own key and have your own key on-prem. And then once it's encrypted, then we can write to the data path, which can be public cloud, which can be a storage node, and we don't care. It's abstracted away, like you saw in the previous slide. So that means that if you have sensitive data that's really important to you, then you can run it through Nooba, through the endpoint. It can get compressed, encrypted, deduped, blah, blah, etc. And it ends up in the public cloud. But if someone would be able to access that data, he or she can't do a single thing with it, because it's just crap what they find there. They cannot decrypt it without having the key, without having access to the Nooba system that runs on your prem. So it's really a nice feature for customers that have data they want to store in public cloud for data gravity reasons, perhaps, and Nooba can make sure that it's not accessible to people who don't have anything to do with the data. I hope this makes a little bit sense. This picture shows it once again. So from an application perspective, on the left side we have an S3 write. The S3 write gets chunked, so it's getting fragmented in little pieces. Then it gets deduped, so everything that's double, so that's similar, that's exactly the same, is being taken out. Excuse me. Then with the residue we can compress that, so we can squeeze it together, then encrypt it, and we can then write it to whatever store we want and replicate things or spread it across multiple locations, perhaps, and the data is secured. So this is what Nooba can do for you, and an example of a use case with multi-cloud gateway using the Nooba technology. I don't know how we're doing in regards to time. Okay, I need to hurry up. OCS is powered by Ceph. What does that mean? What's the benefit of that? So Ceph is actually a software-defined storage system, and we already have that for years inside Red Hat. It's also being used with OpenStack, for instance, and also as an object store. It can be used with AI applications, with data analytics, and so on. Actually, it's a massively scalable system that supports 2 petabytes of data. There is no one single point of failure. Everything is redundant, and the system is completely self-managed and self-healing in order to reduce expensive maintenance windows and so on. Fourth, data is distributed dynamically. This means if we put data onto a Ceph system, it's getting spread across the complete system. It will use everything and all components so that we won't have single point of failures and also no hotspots. That means the data is getting concentrated on one single place. No, it's distributed across the whole system, which ensures that we will, keep performance and so on. Ceph is not something that's here since yesterday. It's already for quite some years a project that's already there for quite some time. Funded in 2003 by Sage Weil, and now it's 2020, and we have incorporated this in our OCS solution. It's proven technology, reliable. And how is it composed? Well, let's start at the bottom of the screen. There's RADOS. RADOS stands for Reliable Autonomous Distributed Object Store. This means that it's actually an object storage system on the internals. In order to be able to access RADOS, to access this reliable object store, you need a library, and this library is a lib to connect to RADOS, and therefore LibraDOS. And this also enables applications that you could actually, if you are a developer, you could write your application that it can directly access RADOS by using this functionality. And the most common program languages are actually supported with this. So if you are into this, then this might be really interesting. On top of that, we have 3 basic functionalities. First is the RGW, and that's the RADOS gateway. What it does is actually it offers an endpoint that delivers S3 storage or Swift storage. And Swift is a dialect of S3, more or less. It's a similar thing. Swift is the open source variety, if you will. That S3 is the commercial thing developed by AWS, by Amazon initially. And it more or less is a proprietary protocol, where Swift is the open version of it. OpenStack uses Swift, and S3 is widely being used in new applications that are running in public clouds, and therefore, adopted and embraced, and we can deliver the same functionality fully compatible. Then there's a thing named RBD, and that stands for RADOS Block Device. And this is actually offering block storage from the same storage solution. So RGW is object, RBD is block, and it can actually offer a block device to a Linux system or to a container running an application that needs block storage. And then there is a component named Cephfs, and Cephfs is actually the distributed file system functionality that's being delivered from Ceph, and that's POSIX compatible, and it's also a scale-out file system. Well, let's have a quick look into these details. So this distribution chain thingy, it looks like a thing from a car engine, but that's actually meant to be the application, and the application connects to the RADOS cluster. RADOS was the reliable autonomous distributed object store, and the different blocks that you see are the OSDs, that are the square ones with the red bar in it. OSD. OSD stands for Object Storage Daemon. It's no more or less than a disk device or an abstraction from that, and that's what we call OSD. The circles are actually the mons. So the mons are the monitors inside Ceph, and monitors take care of the state of the cluster. They know about everything that's going on in the cluster. They are working together, the 3 of them, so they need to have consensus in making their decisions. They use a Paxos way of decision making. So if such a monitor would die or go down, then it will not influence weird things happening in this cluster or trigger weird things, because they always need to have a quorum and they always need to be in consensus with each other before actually something really is decided. And then there's a management or metadata server. Access capabilities, I already talked about it. Block storage, file storage, and objects. That's what we deliver on top of Ceph. And Librados is actually the library that an application could use to connect to the Rados system directly without having to go through a Rados gateway or CephFS or RBD. It can actually directly connect into the internals of Ceph by using Librados. RBD, the block device, I won't spend too much time on this. There are two different block devices. There is kernel RBD and there is the other RBD. The kernel one is the most performant one, but it has less flexibility, and the other RBD is the one that's mostly being used. That's the block device. CephFS has two types of data that it actually has. The data, which is the payload from the application, the actual data, and the metadata is information about that data. That metadata is actually also stored in Rados, so it's also replicated and so on. So it's perfectly reliable, and this is being used for the RWX functionality inside OpenShift container storage. The Rados gateway, it connects to Rados on the south end. It connects to sockets by using Librados, leveraging Librados. And on top, on the north end, it offers a REST API for the application to talk S3. Ceph data is actually placed by something, by a hashing mechanism that's named CRUSH. And CRUSH stands for Controlled Replication Under Scalable Hashing. So that means that every object is getting hashed, and this hash is always the same. Today, tomorrow, next week, next year, over 10 years, it's always the same outcome because it's a hash, and the hash is always delivers the same value. The hash will actually define where an object is getting placed, and it can also be calculated back to retrieve an object. So this is how Ceph places its data, and by using the CRUSH algorithm. And CRUSH can also define how replication takes place. If it's across server system, across racks, or even across data centers, that's all configurable. Another thing that Ceph has is pools and placement groups. So pools are actually logical partitions inside the Ceph system, and placement groups. These define actually where the data in the end will end up, on which OSDs the data will be stored, where it ends, where it's actually stored. So pools, partitions, and placement groups are where the data ends up to. The data is also protected. We can do this in two ways. We can do it with a replication count of 3. That means that every object is written 3 times on different locations, and the CRUSH algorithm defines where those locations are. And there's also another way, that's erasure coding. This is something that we do not yet support inside OCS. So in OCS, it's always a copy count 3, and the erasure coded actually is more or less similar to RAID, but RAID is always limited to one server system, so to one box. There's a RAID controller that addresses disks, but it cannot go outside a machine. Well, erasure coding has more or less similar functionality, but then it's across the network, so it can be spread across multiple systems, and that's more cost effective and for archives and stuff. But for now, it's out of scope. Data distribution, that is actually here is shown how objects are being placed across the entire cluster. So again, there is no hotspot, there is no specific area where all the data ends up from a certain application. So it's always distributed, always being spread by leveraging these placement groups, and placement groups define on which OSD, on which disk the object in the end ends up on. So this was a very fast Ceph 101. There is more information available. If you want to know more about Ceph, feel free to reach out, and we can direct you to other resources and show you more about Ceph, because we can talk for days, so perhaps weeks or months about it, but for now it's way too much. So back to OCS. Let's have a look at the core features. Again, in regards to efficiency, we provide block, file, and object storage. Backup, restore, and clone data is one of the capabilities that's coming along. A consistent experience across multiple infrastructure environments. Security, very important, and therefore built in from the start of the product. We have data encryption at rest, so that means where the data sits, but also in motion. So in transition of data, there's encryption, and also when it's stored, it can also be encrypted. Anonymization and masking of object data, that's what we do with nooban, with the chunking, compressing, encrypting, and deduping. So that's actually masking of data, so that the data is really unusable if you don't have access to the key and to nooban. Integrated management. So in OpenShift, you'll get a dashboard where you can see what's happening with your storage, how you're doing in regards to capacity, performance, and so on. Everything is visible there. We leverage Rook management and Ceph data scale for optimum of data handling. So Rook makes it really simple and easy to set it up and run with the stuff. And Ceph makes it easy to scale enormously with data where needed. And you can still start small, of course. The baseline configuration supports up to 1500 PVs, and PV stands for persistent volume. Remember, that was the top layer that was writable inside a container pod. That's actually we can have 1500 PVs that can connect to that layer, or if you have RWX, even more. One OCS cluster can scale out, and the maximum scale is at this moment 5000 PVs. So out of the box, with 3 nodes, you have 1500. If you need more, you can just scale out. And at this moment, with 4.2, we can go to 5000. But, on the roadmap, there's more to come here. So, OCS. Let's have a look at, how it's the view of the user and the administrator. The administrator manages OCS, and the user uses it in the similar way, actually. So this picture is very good for the comprehension. We have the OCS operator. We'll go into more detail what that does. Actually, the OCS operator takes care of the OCS environment. Yeah, that's maybe logical, but what's inside the OCS environment? There's, of course, Ceph, and Ceph has its own operator, the Rook Ceph operator. That operator just takes care of Ceph. No more, no less. It's just Ceph. And the OCS operator actually enables the Rook operator to do so. Same goes for nooban. Nooban has its own operator that manages nooban. So we have 3 operators, the OCS, and then Ceph and the nooban operator. That's more or less the way that OCS operators are combined. So in the end, we can run on bare metal solution in the future. VMware, at this moment, to be very clear and honest with you, at this moment we can only run on VMware and AWS, but this is broadening, and in next releases we will have more capabilities. So that regardless of where you run, you can run Red Hat OpenShift container storage alongside with Red Hat OpenShift. You will have block storage, file storage, and object storage, and on the south end, so on the lower end, the back end, it just consumes block storage. Like in Amazon, it consumes EBS, and on top of EBS, we provide block, file, and object. Same for VMware. We can use VMware storage, vSAN, and on top of that, we provide block, file, object. While this normally out of the box is only block storage. This is in a nutshell what the solution is about. So we can literally live on whatever kind of infrastructure layer. The same experience applies in all situations. You will end up with block, file, and object storage completely managed, completely taken care of by OpenShift and the operator functionality. Another question that we often get is, how about CSI? Because why would I need OCS? Why would I need Red Hat storage? Because I already have the CSI functionality, and I have my my XYZ system, or my system from vendor X or from vendor Z. So I don't see the benefit. That's something that we very often get confronted with the customer asks, well, why would we need OCS? Because I already have my storage and I don't see the value add. Well, on the left side, in version 4.1, storage was something that was in tree with Kubernetes. So it was actually included in Kubernetes. And that meant that actually, if you would have a storage system, that the driver would need to align to Kubernetes. And if there would be a Kubernetes update, there would also be a need for a new inline storage driver. So that was really, if you have a broad ecosystem, that's really, getting hard. So starting with version 4.2, and I'm talking about OpenShift 4.2, there was this introduction of CSI, and that's the Container Storage Interface. And that's actually a common way of addressing storage systems. So it's the same way of connecting to whatever storage, and that's being taken care of by a plugin. So a storage vendor can have a CSI plugin so that CSI can connect to the plugin and then manage the storage. And in that same regards, we have our OCS plugin. So the OCS plugin actually manage our storage system, but you could have another plugin from another storage vendor. So what's then the reason why you would want to have OCS in specific? Well, if you look at the bottom part of the screen, the first 5 layers, so that's CSI provision, CSI attach, resize, snapshot, clone, period. Those are the 5 basic functionalities that CSI delivers. No more, no less. So that's actually what you could do against a storage system. However, there are more, common persistent volume modes, types, capabilities, whatever you want, and those are, listed on top of that. So A, B, C, D, E, F, etc. There are multiple functionalities besides what CSI can do. So just having CSI is not the same as having all these additional functionalities. For instance, dynamic provisioning, that could be interesting, but also if you need to clean up afterwards, otherwise you will, end up with orphaned storage volumes, for instance, and who knows which volume belong to what, and those kind of things. So there is a lot of additional functionality on top of the basic CSI functionality, and that's very important to know. And then other vendors or other providers may have, a reasonable amount of those kind of functionalities. However, that is only within their context, within their product, within their environment where you use this functionality. Suppose you want to use something else, then chances are pretty high that you will have to buy something new or have to buy another solution because it's only working in their ecosystem. If you look at OCS, for instance, then, like I said before, we can run on whatever infrastructure. There is no vendor lock-in in that regard, so you can use all kind of infrastructure providers and not just one single underlying infrastructure. So this is a huge benefit because you have an infrastructure independent situation where with commercial vendors you often have a specific CSI driver that only works inside their own ecosystem. And as long as you are working with them and you want to stay there and you don't have plans to ever change, then that's perfectly fine. However, if you want to have more flexibility and have more abstraction on top, then you are way more flexible with OCS solution on top of that. I hope this makes sense. It's hard to explain this and also hard to understand. Maybe if you hear these things for the first time, main takeaway is that CSI driver only has basic functionality. On top of that, there is a lot of additional functionality that's not addressed by CSI as such, and depending on the solution that you use, that defines what your flexibility to the future will be if you have a change situation or you want to go onto public cloud or change in whatever way, and then chances are that you're getting stuck in a solution that's only working in that specific ecosystem. I hope this makes sense. I'm not here to bash others or whatever, but just trying to make you understand what the main difference is here. and how you have the most flexibility by staying open and staying open all the way. This is another example of the uniform set of persistent services across any infrastructure. So this means regardless wherever you run, you will have these functionalities, and this is really interesting because you can see that most of the things are addressed with OCS. There's one thing named snapshot clone that says tech preview that will be available in the next version. So just to give you an idea, I will share the slide deck afterwards so that you can have a look at it. We have multiple deployment modes. We can optimize for simplicity. That means that the OCS containers or OCS machines can run on the same worker nodes where your application run. If you want to have a quick setup as a developer to build something really small and neat, then you can use that one. The most common one is actually at this moment number 2, and that's where we have separated OCS nodes, and that means that the storage solution runs on dedicated worker nodes that only run the container storage solution, and that the works where the application run are separate. So with a minimum of 3, then the storage is separated off from the worker nodes. The benefit of this is that you can use the full capacity and resources of the worker nodes to run your applications on, and they are not consumed by storage. But for easy setup, then it could be a different story. Number 3 is optimized for scale, and that's a future one, and that is actually meant independent mode, and that means that the storage is completely separated off the OpenShift cluster. It lives outside the OpenShift cluster, and it can scale independently. So in this way, you can scale your storage independent from the OpenShift cluster. In next versions, you can have multiple OpenShift clusters connecting to the same storage that can scale independently. And this is really something useful, and lots of customers are asking us for this kind of functionality so that you actually can scale for specific workloads here. So I won't spend too much time on this in regards to time because it's already getting tricky in regards to time. About the operators, the components that OCS use, there's a primary operator, the meta operator. What it does, it facilitates the other OCS operators like Ceph, Rook, Ceph, and nooban by doing their tasks. So having said this, that means that Rook is specifically for managing Ceph and only this and no more. And in order to use it in OCS, there is a meta operator that actually addresses the Rook Ceph operator and makes it possible to run in OCS context. So it also watches the other operators and it configures their custom resources. So actually, it's the operator that has an overview on what the other operators are doing. It manages them and creates resources for them. So that is the primary operator that Red Hat OpenShift Container Storage uses. We also use the OpenShift Machine API, and the Machine API actually takes care of node host provisioning after we set up the cluster. So if you set up a cluster, the Machine API will take care of the node, it will provision it, and then this way you have a capability for an elastic dynamic provisioning methodology. There are 2 primary resources in the Machine API. Machines, of course, those are the machines themselves. They describe the host type for the node. So if you run in public cloud, it describes what the host would look like for a node. And machine sets are, like container pods. They are groups of machines, and they act like replicas. So you can scale them up and scale them down. You can actually easily scale with machine sets, similar like you do with a container pod in a similar kind of way. So if we go into the machine set in somewhat more detail, there is metadata that has information about the machine set, what the name of the machine set is, and other relevant labels like node names, etc. And there's a selector that defines which machines are associated to the machine set. That's defined by the selector. And then there's a template that has metadata about machines' properties, details, location. There's a spec section contains how the machine is created, how it's built up, and the provider spec is something specific to the provider, which could be AWS, and it has, provider-specific information for this machine set, like AMI ID, machine type, etc. OCS runs on an administrator-selected machine set, so that means that we point out the machines that we want OCS to use. That's being done by a UI, and then we can also set taints on those machines. And what the benefit of a taint is actually that it allows for a node to control which pods should or should not be scheduled on that node. In the case of OCS, only storage-related pods are allowed by the taint. So if we have an OCS worker node, we can set a taint on it, and that taint will actually make sure that only storage pods are running there. And there is a huge benefit here, because if you do this, then you only have to pay for the OCS subscription, and you don't pay for OpenShift worker node. So because only storage runs on it, you don't have to pay OpenShift subscription for that specific node where storage runs on. I hope that makes sense. It really goes fast now. If you want to know more, you can always reach out, and we can pleasure to help you and whatever to give more information on it. Okay, so in regards to sizing, there are some guidelines here to be aware of. The minimum amount of storage nodes is actually 3 nodes. So that's the minimum amount that you need for OCS to run. And out of the box, with these 3 nodes, we support up to 1500 persistent volumes. That means with these 3 nodes, you can provide 1500 volumes to containers or container pods. Each additional node on top of that enables for 500 additional PVs. However, we work in a replication count of 3, and it would make a lot of sense to start with 3, then have 6 nodes, then have 9 nodes. However, the maximum number is 10, and the maximum number of persistent volumes with 10 nodes would be 5,000 persistent volumes. So, key takeaways: minimum amount is 3. With the minimum amount, you will have capability for 1500 persistent volumes. If you add nodes onto that, each additional node enables you for an additional 500 PVs on top. So that would theoretically mean that 4 nodes would offer 2000 PVs, 5 nodes 2500, etc., etc. So subscriptions, I already mentioned about it. OCS nodes, so if you have dedicated OpenShift container storage nodes, they will not be counted against OCP, OpenShift Container Platform subscriptions, OpenShift subscriptions. So that means that a customer only pays for OCS SKUs, and he does not pay for OpenShift SKUs on the pieces where the storage runs on. So OCS socket pairs are only for OCS nodes in that regards. This means that there is no dual cost. So if you would use whatever storage solution from whatever vendor, then it most of the times runs on a worker node, and that means that you have to pay A for the worker node, B for the storage solution of your provider that runs on that worker node. So that's a dual cost. If you use OCS, then you only pay for the storage and not double for storage and OpenShift, because the OpenShift cost is, defeated away. You only pay for storage. I hope this makes sense. So this is a big benefit, actually, if you compare that to other storage solutions where you have to pay double. This brings me on to the roadmap section. We are now at version 4.2. Version 4.3 is actually at this moment planned for mid-March. I'm not giving any guarantees here. It could be that, something happens and that we have to wait on stuff. Anyway, this is an indication for you at this moment. So 4.3 planned for mid-March. The things that are being addressed are flexibility and deployment, AWS i3 instance. So this means that you can run it on a lower skilled resource, hence lower cost in operational cost. Flexible OSD size. At this moment in 4.2 it's fixed. It's fixed onto 2 terabyte. In 4.3 you will have more flexibility, so you can have other OSD sizes there. OSD are the basic parts in the Ceph storage. Also is planned for local storage in both VM and AWS. That means you could use local storage on the nodes. For now it's in VMware it uses vSAN, and in AWS it uses EBS. And in this version we will enable for local storage coming from server systems. Data portability across hybrid cloud is a thing. There will be new functionality. Stretch cluster is something that comes along in tech preview. Same for bare metal. Stretch cluster is something that's asked a lot for in the region here where I live, in the EMEA region. There are lots of stretch situations. There will be a tech preview thing for that. Multi-cloud gateway will get new functionality, auto-scale, performance, IBM cloud objects support, and the bucket policy announcements there. Then switching on to 4.4, planned for mid-May this year. Support for Azure and for bare metal. Remember I mentioned that it was at this moment AWS and VMware. Then we will open it up for Azure, bare metal, and maybe other infrastructure providers. Independent mode, that means that OpenShift Container Storage lives outside OpenShift, where you could scale separately, where you could scale apart from your OpenShift cluster, could scale the storage. Snapshots, clone, restore, tech preview planned for mid-May, scale to 10,000 PVs. Remember in the previous slide I said there were a maximum of 5,000 PVs at this moment. This is going to get double in version 4.4. FIPS crypto validation also being asked for by customers. OCP compact mode, and this is a special use case where you run on 3 master nodes that contain the whole bunch of functionality for specific use cases. That's named compact mode. PV encryption, so that's encryption of persistent volumes. Multi-cloud gateway, warm tech preview. That means that warm is write once, read many, write your data once. It will not change afterwards, and this is new functionality coming along. Some stuff like the snapshots, clone, restore depend on Kubernetes API stability, which is currently still in beta, and we are dependent on that. So no real guarantees here at this moment. Longer term, Google, IBM Cloud, Ref also being asked for. Another thing that I'm being asked sometimes is why does Red Hat support VMware and why can't I run on Ref yet? This is because there are huge amounts of VMware users, customers that use VMware and want to use OpenShift and OpenShift Container Storage, and then this is now possible. Ref will follow on later. Sharing OCS storage across multiple clusters, multiple storage pools, so having multiple storage pools that are to be addressed. Snapshot, clone, and restore, which was tech preview in 4.4, will be general available GA in 4.5. Same for stretch cluster, and then active passive and active passive sharing of object stores. That's all multi-cloud gateway functionality being broadened in future release. PV resize means actually a resize of the persistent volume. Now you issue a persistent volume and the size is fixed. In that version you are able to resize. Multi-cluster DR and KMS support key management system support. I'm almost done. I'm over time, but just wanted to show you, those are some slides. I can go through it really quick. It's how OCS is actually being installed, the steps that you need to take to install OpenShift Container Storage. So it's really in a summary. Inside OpenShift, you browse to the operator section, you go to the operator hub, and then you search for storage and select OpenShift Container Storage by Red Hat, and click on install on the screen below. Once you click that button, then you need to set some additional parameters. First of all, it will ask you where you want to install the storage. Would you install it in all namespaces, or do you want to have a specific namespace? In this example, and it's the recommended way, we have a namespace named OpenShift Storage. The update channel is stable for 2. We can define whether we want to have automatic updates or do it manual. So this is all configurable, and at the end of the road you click subscribe. So once you did that, then it will be actually, the operator will be installed. And you can see that by browsing to the operator section again, and then go to installed operators. And then you will see OpenShift container storage, tada, for the 2.1. You can click on that, click on this OpenShift container storage item, and then we can dive into the details of the operator. We browse to a button named Storage Cluster, which is on the top of the screen, or more to the middle. If you look at installed operators and then follow that line, then you see somewhere Storage Cluster, browse to it, and then once you activate that, you will see a button named OCS Cluster Servers and create OCS Cluster Servers. Well, obvious, click on that one. And then that's the moment where you are able to select the machines where you want to run OCS on. That needs to be a worker machine. You can have dedicated workers for that, or run it co-resident on workers that also run applications. Select out the machines, and finally click on Create. Magic happens, and the installation is done. So then you know, your OCS environment has been installed and is ready for usage. How do we check up if everything went well? We can go to the dashboard and look at the persistent storage tab, and then it will show at health OCS storage cluster is healthy. To be honest, this is slide where, because in real life it will take a few minutes. It can take up to 5 to 10 minutes before everything is ready and able. So as you saw in this example, here it's all running, and this is how you can check whether your persistent storage is running or not. Same for the object servers, for the multi-cloud gateway. There's also a dashboard, and this one says object storage is healthy. Well, that's always the good news. Finally, you can, as a final check, you can look at the storage the storage section and then browse for storage classes. You could also do OC get SC from the command line, and then you will notice that you will have 3 additional storage classes. 1 for block, 1 for file, and 1 for object. And this actually completes my presentation for today. I would thank you all a lot for, listening to this stuff and joining us. And if you have any questions, feel free to reach out to us. We're more than happy to help you. I hope it was useful. Wishing you a very good day. Thanks a lot. Signing off. Bye-bye.